Hi everyone, welcome back to Chem Help ASAP. In today's video, we're going to be talking about electrolytic cells. Let's get started. An electrolytic cell is exactly opposite from a galvanic cell. This is a cell where we have to apply an external current to force the reaction to proceed. So our current is going to run from right to left. Our anode and cathode is also switched. So our cathode is going to be on the left. It is still tied to our reduction, however. Our anode is going to be on the right, and it is still tied to the oxidation. Cations and anions also flip how they run in an electrolytic cell versus a galvanic cell. Our cations are going to move left to the cathode, and our anions are going to move right to the anode. Let's take a look at a particular cell. So first, I'm going to take a look at the galvanic cell for this silver and zinc reaction. An E cell for this galvanic cell is 1.56. Now, to make this an electrolytic cell, I need to force it to run in reverse. So you can see my reactants here were my products in my galvanic cell and vice versa. My reactants in my galvanic cell are now my products. My E cell is the same value, but now it has a negative sign in front, which means that for this electrolytic cell to run, I need to apply a current that is greater than 1.56 volts. Let's also write in a little more detail as to what's going on the cathode and the anode. In my electrolytic cell, my zinc is being reduced to zinc metal. So I'm going to make the electrode zinc, and my zinc cations in solution are being reduced to zinc metal. Of course, the opposite is happening at the oxidation, making this electrode silver. My silver metal is being oxidized to silver cations. And again, for my current, I need to run a current that is greater than 1.56 volts to make this electrolytic cell run. Let's take a look at another electrolytic cell. This problem reads, a current of 0.3 volts is run in the following electrolytic cell. Will the redox reaction proceed? And here is our balanced redox equation. Remember, for an electrolytic cell to run, you have to run a voltage that is greater than your E cell that you would calculate for a galvanic cell. So let's start with a calculation based on this redox equation for a galvanic cell where our E cell is going to be positive. Here on the right is a table with many half reactions. We just need to identify which half reactions are happening in our overall reaction. Well, I can definitely see that I have an iron half reaction happening. It looks like my iron 3 is being reduced to iron 2, and that is going to be this reaction right here. The other half reaction that is happening is between my manganese and my manganese oxide, and here is that half reaction right here. So let's pull these out along with their reduction potentials. So here are my two half reactions that make up my overall reaction. Again, for calculating E cell, I'm going to calculate it like it's a galvanic cell, knowing that I will have to put a negative in front of it for the electrolytic cell. Here is how I'm going to calculate E cell. This is going to be my manganese minus my iron. That is going to be 1.23 volts minus 0.77 volts, which gives me an E cell of 0.46 volts. Remember, your electrolytic cell needs a current greater than 0.46 volts to run. So if I am running a current of 0.3 volts, this electrolytic cell will not run. I am not running enough of a current. So even though this problem specifies an electrolytic cell, I find it is easier to treat it at first like a galvanic cell just to get your value for E cell. And then once you have your E cell, you can compare it to your voltage and see if it will run like an electrolytic cell. I hope you found this video helpful, and thanks so much for watching.